let's leave proteins behind and move back to DNA. One of the really, really important technologies of the 20th century is PCR. And PCR is a rapid amplification. It's polymerase chain reaction that is more directed than random fragmentation. So instead of randomly shearing DNA into pieces and hopefully you get the right size, it contains the right thing you want, with PCR, theoretically, you should be able to amplify the exact sequence you want and have billions of copies of it after the reaction is over. There are some limitations when designing an experiment with PCR and trying to perform PCR. The first is that PCR would work best if some of the sequence is known, at least what's called the flanking regions. So if you have your gene of interest, let's see here, if I can get my pen. You have a gene of interest. This is your, there we go. Drawing with a mouse is hard. This is your favorite gene, and you want to amplify it and get lots of copies. It's helpful if you at least know some of the sequence up here and up here, because that would allow you to design a primer so you could amplify this way and design another primer so that you could amplify this way. Right. And I think you've probably talked about PCR before, so hopefully that's not, totally a new concept for you. The other kind of limitation is the idea that your fragments are going to be limited in size. Some of the best PCRs, you may get up to 2,000 base pairs, but it can be tricky to amplify things that start to get bigger than this. So for genes that are really large, it could be challenging to amplify them all in one go. You may have to amplify the gene in steps and try to piece it back together. Okay. What are the major steps of PCR? So hopefully in your head, you're maybe thinking about some of these major steps, reviewing them from previous courses, but of course I'm going to show them to you and we can talk about them as well. The first major step is to denature the DNA. So you usually heat up the DNA to a high temperature, like 94, 95, and the two strands would come apart. This is what we mean by denature. So the hydrogen bonds that hold the bases together come apart. The second step is annealing. We decrease the temperature quite a bit, not enough that the two strands come together, but enough that our primers would stick to their complementary regions on the DNA. And then our third step, we warm it up to the ideal temperature for our DNA polymerase, and we get extension. So the DNA polymerase adds in these nucleotides and builds our growing strands. So again, we have the denaturation, very important to separate out. We have the annealing to allow our primers to bind. And then we have the extension step in order to generate our two new sequences, or our two new strands, Same sequence, just two new strands. And then we go back to the beginning and do it again. Generally, we'll do this 30 to 40 times. And this, if you add up the time, you can alter these times a little bit, but a general standard PCR will take anywhere from 2 to 3 hours, which is pretty quick to go from one piece of DNA to billions of pieces of DNA.
Hi, and welcome to my science lab. In this video, we will introduce the basics of the polymerase chain reaction, or PCR. We'll review the history of PCR, typical components and principles of the reaction, PCR reaction types, polymerases available, and various applications of this widely used molecular biology technique. What is PCR? It's one of the most common techniques used in molecular biology. It is a quick way to amplify minute quantities of DNA to obtain millions of copies of DNA molecules. DNA polymerases used in PCR originate from thermophilic microorganisms and therefore are heat resistant. Their ability to withstand high temperatures is important in PCR because high temperatures are needed to melt or separate the double-stranded DNA. This separation then allows the DNA polymerase to synthesize complementary DNA strands. The technique was first published in 1985, and a Nobel Prize was awarded to Kary Mullis for his invention of the PCR method. Researchers had been performing similar reactions since 1971, when Norwegian scientist Kjell Kleppe and colleagues described an enzymatic process to replicate a short DNA template using primers in vitro. In 1988, the first PCR machine was introduced to the market. Since then, many improvements have been made to the reagents and instrumentation researchers use to perform PCR. These improvements in PCR technology have allowed for powerful achievements with far-reaching implications, such as sequencing of the first complete individual human genome. Thanks for watching.
All right, so that's kind of how PCR works. And this is actually really funny. I know this person. I used to work with him at Fresno State. All right. So the major components in a PCR tube, hopefully you remember them, but you definitely are going to need template DNA. So you need the DNA that you're going to amplify. You need primers, because primers are important for you to be able to have DNA polymerase to have a place to sit and to know where to sit. You need DNA polymerase, and it needs to be a thermostable DNA polymerase that works at very high temperatures. You need nucleotides, the dNTPs, for DNA polymerase to use for extension. And you may add things like magnesium chloride, water, etc. But you've got to have a template, you've got to have primers, you've got to have an enzyme, and you've got to have nucleotides. Those are the major things that you need. So the question becomes, where do you get primers? How do you know what primer sequence to use? And why is Taq polymerase so special? Well, where you get primers is pretty easy. You buy them from any one of a number of companies that will sell them. And again, they're relatively inexpensive. How do you know what primer sequence to use? That gets a little trickier. It is helpful if you either know the flanking region. Let's say you want to amplify a mouse gene. You want to amplify a mouse gene, and you know the human sequence. Maybe you could use the human sequence to design primers that would amplify the mouse sequence, because they're probably going to be pretty close. Or if the mouse genome is sequenced, you can just use the mouse genome sequence instead. And then why is Taq polymerase so special or important? Because it works at high temperatures. So it's a DNA polymerase that will work at very high temperatures. So for basic PCR, you have to have enough knowledge of the surrounding area to design a pair of primers. In an ideal world, whatever gene you're interested in, that genome has been sequenced. So you could use the known genome sequence to design your primers to amplify your gene of interest. Let's say things are not perfect, not a perfect world, and your species has not been sequenced. So the example here, the human spectrin gene has been cloned and sequenced. but perhaps you want to amplify the mouse spectrin gene. So in this case, what you could theoretically do is take the information from the human gene and use it to design primers for the mouse. Is the mouse sequence going to be identical to the human sequence? Maybe. Maybe it's that highly conserved. But maybe not. Maybe there are going to be some base pair differences in that region between humans and mice. So if we go back and look at our standard PCR, right, our standard formula here, what do we modify in order to perhaps use human primers to amplify a mouse gene? I'll give you a couple seconds to think about it. Remember when we talked about cDNA libraries and we talked about probing a cDNA library and changing the stringency? What we would do in this situation, if you are using human primers to amplify a mouse gene or any other mismatched set of primers, to alter the stringency, you change the temperature at which the primers anneal. If you increase the temperature, you increase the stringency. So if you were doing human to human, you might increase this by a few degrees. If you're doing human to mouse, you may need to allow for a few mismatches, so you might decrease the temperature by a few degrees. So that's really important to think about when you're designing experiments, and as an application of PCR, how would you modify the conditions of PCR to get the best results possible?